right now, tonight, as you pull the blankets a little closer and the room settles into quiet around you. There is a planet in our sky doing something that should not be physically possible. Venus is spinning backwards. Not tilted, not wobbling, not rotating in an unusual direction relative to some obscure reference frame. Backwards. Opposite to every other planet in the solar system, if you were standing on the surface of Venus tonight, the sun would rise in the west. It would crawl across the sky so slowly that months would pass before it reached the east, and a single Venusian day, one complete rotation, would take longer than a full Venusian year. The planet completes its orbit around the sun before it finishes a single spin. Every other planet in our solar system inherited the same direction of rotation from the spinning cloud of gas and dust that formed everything. Mercury spins counterclockwise. Mars spins counterclockwise. Jupiter, so massive it could swallow more than 1,300 Earths, spins counterclockwise so fast its equator bulges outward from the centrifugal force. Saturn, Uranus, Neptune, all of them turning the same inherited way. The rotation of a solar system is a birthright, a physical signature that traces back to the first moment a cloud of gas began to collapse under its own gravity 5 billion years ago. Venus did not keep its birthright. Something took it, something enormous and violent and now almost completely erased from the record. And tonight, slowly, in the quiet, we're going to trace what happened, one careful step at a time, until the answer arrives on its own. We will go through what the solar system's original spin actually means and why Venus breaking it is so strange. We will follow the two catastrophic theories scientists have built to explain it. We will walk through what Venus looks like now, a world of melting rock and crushing silence, and with what it might have looked like before everything changed. We will sit with what it means that two identical worlds began the same way and ended somewhere unrecognizably different. And we will land somewhere honest about what the angle of one ancient collision means for everything that came after it. If these slow, careful walks through the universe are what help you settle into the night, I would be ever so grateful if you subscribed. It is a simple thing, but it helps this channel reach more people who might need exactly this kind of quiet. Now then, get comfortable. Let your shoulders drop. We begin. You have probably seen a diagram of the solar system at some point in your life. Maybe pinned to a classroom wall. Maybe in a library book with glossy pages and photographs from the Voyager missions. 8 planets in their lanes, the sun at the center, everything arranged with the clean tidiness that educational materials prefer. That diagram almost certainly showed the planets orbiting the sun counterclockwise when viewed from above the North Pole, and it almost certainly did not explain why. It simply showed them going that way, the way all diagrams do, the way all the planets do. Because that is how it has always been, and there does not seem to be anything that demands an explanation. That understanding is not wrong. It is just missing something that changes everything. The direction of rotation in our solar system is not a coincidence. It is not an arbitrary choice that could just as easily have gone the other way. It is the physical record of a single event that happened 5 billion years ago, preserved in the motion of every planet, every moon, every asteroid and comet and chunk of ice still orbiting today. And once you understand what that record is and where it comes from, the fact that Venus has broken it becomes one of the most quietly disturbing things in all of planetary science. So let us start at the actual beginning. 5 billion years ago, in a region of the Milky Way that would eventually become our neighborhood, there was a cloud. Scientists call it the solar nebula, the cloud of gas and dust that gave birth to the sun and everything that orbits it. The solar nebula was not a neat spherical thing. It was irregular, vast, slowly moving, not because anything was pushing it, but because in space everything with mass interacts gravitationally with everything else, and all of those tiny pulls had given the cloud a very slight, very gentle rotation. Think about what happens when water drains from a very large, very still bathtub. Even if you cannot see the motion at first, the water is already rotating as it moves toward the drain. The rotation was in the water before you pulled the plug. All the drain does is reveal it by concentrating it. As the water spirals inward, the spin becomes more visible, more organized, faster near the center. The solar nebula did exactly this. but across distances that make the bathtub analogy almost embarrassing to use. Over millions of years, gravity pulled the nebula inward. As it collapsed, it spun faster. The spin that had been almost imperceptible across trillions of miles of gas and dust became concentrated, organized, defined. The cloud flattened into a rotating disk, the same shape you see in every image of a forming solar system, and at its center, material piled up and compressed until the pressure ignited nuclear fusion. The sun was born. Conservation of angular momentum is the science word for what happened next. Angular momentum is the stored energy of rotation, and it obeys one rule above all others. In a closed system, it cannot be created or destroyed, only moved around. Here is what that looks like in your living room. Think of a figure skater in the middle of a spin. When they pull their arms in tight against their body, they speed up dramatically, sometimes so fast it becomes difficult to watch. When they spread their arms wide, they slow to something almost stately. They are not adding energy from outside. They have not plugged themselves into a wall. They are redistributing the angular momentum they already have. Pulling in reduces the distance between mass and the axis of rotation, so the rotation speeds up to compensate. Spreading out increases that distance, and the rotation slows. The collapsing solar nebula did this on an incomprehensible scale. The spin that had been distributed across trillions of miles concentrated into a disk a few 100 million miles across. The rotation accelerated, and everything that formed within that spinning disk, every planet, every moon, every rock that eventually found a stable orbit, inherited a piece of that original rotation. They all spun the same direction because the angular momentum of the parent cloud had a direction, and it was passed down to every child. This is not something we inferred by analogy. We have measured it directly in the structure of other solar systems currently forming. The Atacama Large Millimeter Array, a network of 66 radio telescopes in the Chilean desert that can image structures at distances of hundreds of light years, has photographed dozens of protoplanetary disks forming around young stars. In every case where the disk is clearly resolved, it is rotating, always in a single direction, always reflecting the angular momentum of the parent cloud that collapsed to form it. What we are observing in those images is the same process that happened here 5 billion years ago, playing out around other stars in real time. The inheritance is universal. It is not something specific to our solar system. It is the way solar systems form, and that makes Venus not merely a local curiosity, it makes Venus a violation of a process that plays out identically around stars across the entire galaxy. Here is what that means at the most extreme scale. There are estimated to be somewhere between 100 and 400 billion stars in the Milky Way. The best current estimates suggest that most of them have planetary systems. If the inheritance of rotation from the parent cloud is as universal as our observations suggest, then there are somewhere between tens of billions and hundreds of billions in planetary systems in our galaxy alone, all of whose planets spin in the inherited direction of their birth cloud. Venus is the exception. In our solar system, possibly in many solar systems, at least one world received enough of a disruption to break the pattern, and we live next door to the only example of this we have ever been able to study closely. Now extend that to the extreme case. Jupiter, the largest planet in our solar system, contains more than twice the mass of all other planets combined. It is so massive that the point around which both Jupiter and the Sun truly orbit, the barycenter of the Jupiter-Sun system, lies just outside the surface of the Sun itself. Technically, Jupiter does not orbit the Sun. Both bodies orbit a shared point in space, and Jupiter rotates counterclockwise in 9 hours and 56 minutes. A day on Jupiter is shorter than the flight time from London to Sydney. The rotation is so fast that the equatorial diameter is 9,275 kilometers larger than the polar diameter. The planet is visibly oblate, flattened at the poles and bulging at the equator, squeezed by its own speed. The Great Red Spot, a storm system 3 times the size of Earth, has been spinning continuously inside that atmosphere for at least 350 years of recorded observation and possibly for much longer. All of that rotation traces back to the same original cloud that Venus came from. What this means for you specifically right now is this: the room you are in, the planet beneath you, the rotation that makes your day and night, the tilt that gives you your seasons, The angular momentum that has been preserved in Earth's spin for 5 billion years. All of it is a piece of the same inheritance that every other planet in this system carries. You are living on the preserved record of a cloud that collapsed 5 billion years ago. The rotation of the Earth beneath you is the last echo of that collapse, still ringing, still measurable, still real. Venus lost its echo, and we're going to find out how. Now extend that to the extreme case. Jupiter, the largest planet in our solar system, contains more than twice the mass of all other planets combined. It is so massive that it does not quite orbit the Sun. Both Jupiter and the Sun orbit a point called the barycenter that lies just outside the Sun's surface, and Jupiter rotates counterclockwise in 9 hours and 56 minutes. A day on Jupiter is shorter than the time it takes to fly from London to New York. The rotation is so fast that the equatorial diameter is 9,275 kilometers larger than the polar diameter. The planet is visibly squashed, flattened by its own spin. The Great Red Storm, a storm system 3 times the size of Earth, has been spinning inside that fast-rotating atmosphere for at least 350 years, and possibly for much longer. All of that rotation, all of that angular momentum traces back to the same original cloud. Sit with that for a moment. Saturn, Uranus, Neptune, all counterclockwise. Mercury counterclockwise. Mercury counterclockwise. Mars counterclockwise. Even Earth, tilted 4 degrees from a collision we will come to shortly, still spins counterclockwise when viewed from above. The rotation of the planets is not incidental. It is inheritance. It is physics writing its own autobiography across billions of years of time in the motion of worlds too large to move by any other means. And then there is Venus. Venus rotates clockwise. One complete rotation takes 2043 Earth days. To put that slowness in something concrete, if you drew a red dot on the side of Venus facing you right now, that dot would take 243 days to rotate around and return to where you are standing. In that same time, Jupiter, the largest planet, would have completed more than 35,000 full rotations. Jupiter would have spun over 35,000 times while Venus turned around once. But is not just the speed, the direction is what changes everything. Venus is turning the wrong way, against the rotation that every other body in the solar system inherited, as if something reached in and physically reversed the spin of an entire world. A single Venusian day is longer than a Venusian year. Venus takes 225 Earth days to complete one orbit around the Sun, but 243 Earth days to complete one rotation. If you were living on Venus, you would celebrate a birthday, a full trip around the Sun, before the Sun had moved meaningfully across the Venusian sky. The calendar and the clock have been inverted. The orbit outruns the spin. Angular momentum does not reverse itself. This is not a philosophical claim. It is a physical one. It is as foundational as the statement that objects do not spontaneously begin moving without a force acting on them. For Venus's rotation to have reversed, something external had to act on it. Something with enough energy to overcome billions of years of inherited counterclockwise rotation and physically redirect an entire planet. The question is not whether something happened. The physics makes that certain. The question is what it was, and whether we can still find the evidence, and what it means that a world identical to ours received it while ours did not. Let that settle before we go further. Here is the full weight of what we have just established. 5 billion years ago, a cloud of gas and dust collapsed under gravity. It had a slight rotation, barely perceptible across the trillions of miles of its extent. That rotation was preserved as the cloud collapsed, concentrated into a disk and transmitted to every body that formed from the disk. Every planet carries that original rotation today. It is not a preference or a tendency. It is a physical law playing out across the full span of solar system history. And Venus, a world almost exactly the size of Earth, formed from the same disk, carrying the same inheritance, has had that inheritance taken from it. Something acted on Venus with enough energy to reverse what 5 billion years of angular momentum inheritance had established, and the only evidence that this happened is the slow, clockwise turn we can measure from Earth, and the physics that tells us it could not have happened any other way. The sky above you right now holds both of these things simultaneously. Jupiter turning counterclockwise in 9 hours and 56 minutes, exactly as expected, carrying the perfect angular momentum record of the solar nebula's collapse. And Venus, the brightest object after the Moon, turning clockwise in 243 days, the wreckage of something that physics alone cannot fully explain without invoking a catastrophe that left almost no evidence behind. We see the outcome. We understand the physics. We cannot see the event. And that is why it is worth going forward into the theories. Not because certainty is available, it is not, but because following the physics of what could have produced this outcome is one of the most honest things science can do with a question that cannot yet be fully answered. Most people who encounter the planet Venus for the first time imagine it as a naturally hostile world, a place that was always going to be what it is, built for hostility the way a deep-sea trench is built for pressure, or the way a desert is built for thirst. Alien in origin, alien in character, alien in every measurement that matters. This is not the case. Venus is not alien. Venus is almost exactly Earth. And the fact that it is not Earth anymore is the most quietly disturbing thing about it. Here are the raw numbers. Venus has a diameter of 12,104 kilometers. Earth has a diameter of 12,742 kilometers. The difference is 638 kilometers. To make that feel like something, 638 kilometers is approximately the distance from Paris to Berlin. In planetary terms, this is nothing. They are the same size. Venus has a mass about 81.5% of Earth's, closer in mass to Earth than any other body in the solar system. Its bulk composition is similar: rock, iron core, silicate mantle. It formed from the same general region of the solar nebula at roughly the same time, out of the same raw ingredients. For decades, planetary scientists called Venus Earth's twin. They did not mean it loosely or poetically. They meant it the way scientists mean things when they use a word carefully. Here is a world that by every gross measurement available is the same as our own. Now here is where the twin diverges. Earth has liquid water covering 71% of its surface. Oceans deep enough in places to submerge the entire Himalayan range without a summit breaking the waterline. Venus has no liquid water, none detectable by any instrument ever sent there. Not a lake, not a river, not a puddle of standing rain anywhere on a surface that stretches 460 million square kilometers. The surface of Venus is completely dry in a way that feels total and permanent. Earth's average surface temperature is about 15 degrees Celsius, warm enough for liquid water, cold enough for ice at the poles, variable enough across latitude and season to produce every climate from tropical rainforest to subarctic tundra. Venus has an average surface temperature of 465 degrees Celsius. The melting point of lead is 327 degrees Celsius. The melting point of zinc is 420 degrees Celsius. The melting point of zinc is 420 degrees. On Venus, both of those metals are liquid. If you set a block of tin, the kind used in the solder that joins the components inside the phone or computer near you right now, on the Venusian surface, it would pool into liquid in the time it takes you to step back. Here is what that temperature means, in a progression that lands differently than a single number. At 100 degrees Celsius, water boils. You know this from a kettle, from a pot of pasta, from a thermometer that has reached its upper limit on a hot day. At 200 degrees, a standard kitchen oven at full blast is somewhere near this temperature, hot enough to bake bread in minutes, hot enough to cause immediate burns on contact with skin. At 300 degrees, you are in the range of industrial kilns used for some ceramic work, or the surface temperature of a cast iron skillet pushed beyond anything a recipe would recommend. At 400 degrees, you are above the auto-ignition temperature of wood, the temperature at which wood begins to burn without a flame touching it. Paper ignites at around 233 degrees. At 400 degrees, paper does not need a match. It simply catches. At 465 degrees, you are on the surface of Venus. The rocks are not glowing. They are not visibly molten. But everything you carry with you, every polymer, every synthetic fiber, every piece of electronics, every metal below aluminium on the melting point scale, is either liquid, burning, or approaching one of those states. The hottest temperature ever recorded on Earth's surface is 56, 7 degrees Celsius at Furnace Creek in Death Valley in 1913. The surface of Venus is 8 times hotter than the hottest moment ever measured anywhere on this planet. Not 8 degrees hotter, 8 times hotter. The scale of the difference is not a matter of degree. It is a different category of temperature entirely. And this temperature is not the result of Venus being closer to the Sun. This point is important enough to state directly, because the intuition that nearness to the Sun explains Venus's heat is wrong. Mercury is closer to the Sun than Venus. Mercury orbits at about 39% of Earth's distance, while Venus orbits at 72%. Mercury's dayside temperature reaches about 430 degrees Celsius, which is actually lower than Venus's average surface temperature of 465 degrees. Mercury is closer and cooler. Venus is further and hotter. The heat is not from proximity, it is from the atmosphere, from the carbon dioxide that traps outgoing heat the way a glass greenhouse traps warmth on a cold morning. Except at a scale and density that has been running for billions of years and has nowhere to dissipate. The greenhouse effect is the term, and it is worth stating precisely. Carbon dioxide in the atmosphere absorbs infrared radiation heat that would otherwise radiate away from the planet into space. The carbon dioxide re-emits this radiation in all directions, including back toward the surface. The surface heats further. It radiates more infrared. The atmosphere absorbs and re-emits more of it. The cycle does not have a natural upper limit until the heat input from the Sun and the heat loss through the atmosphere balance at a new, much higher temperature. On Earth, carbon dioxide makes up about 0.04% of the atmosphere. On Venus, it makes up 96.5%. The greenhouse effect on Venus is not analogous to the greenhouse effect on Earth in any meaningful quantitative sense. It is the same physics running in a completely different regime. Earth's atmospheric pressure at sea level is about 101 kilopascals. Comfortable for a human body. Manageable for architecture, for vehicles, for every structure we have ever built. For every structure we have ever built, Venus's atmospheric pressure at the surface is about 9,200 kilopascals. That is 90 times Earth's. To feel that number in something familiar, the pressure at a depth of 900 meters beneath Earth's ocean surface is roughly equivalent. At 900 meters underwater, every square centimeter of your body is being pressed by a column of water 900 meters tall. On Venus, the air itself does this. Not the ground beneath you, not a column of water above you, the air sitting still. Earth's atmosphere is 78% nitrogen and 21% oxygen, a mixture that has been stable enough for complex aerobic life to evolve and depend on it for the last 500 million years. Venus's atmosphere is 96.5% carbon dioxide, with cloud layers of concentrated sulfuric acid beginning about 45 kilometers above the surface and extending to about 65 kilometers. Not the thin, diluted sulfuric acid of acid rain on Earth, where the concentration is measured in parts per million. Concentrated sulfuric acid, the kind used in industrial processes, the kind that requires sealed containers and chemical safety protocols. The clouds that wrap Venus completely, hiding its surface from every optical telescope ever pointed at it, are made of this. Take a breath here. Let those numbers settle as separate things rather than as a list. 2 twins, same size, same birth, same neighborhood, same starting ingredients. One of them, liquid water, breathable air, an average day warm enough to wear a light jacket, 8 billion people and 400,000 species of plant, and the quiet room you are lying in right now. The other, concentrated acid clouds, air that crushes at the equivalent of 900 meters underwater, temperature that melts the metals in your electronics, and a surface no human probe has survived for longer than 2 hours. The difference between those two worlds is not fundamental. It is not the kind of difference you find between Earth and Mercury, where the raw sizes and orbital positions and internal compositions make comparison almost meaningless. Earth and Venus started from the same place and ended somewhere completely unrecognizable, and the reason that happened is not mysterious at the level of physics. We understand the greenhouse effect that drove Venus to what it is, the runaway feedback that evaporated the water and thickened the atmosphere, and trapped the heat until the equilibrium calcified at 465 degrees. What we do not fully understand is the original trigger, What started Venus down that path while Earth went the other way? What event or sequence of events in the early solar system separated two identical worlds so completely that one cannot support a metal probe for more than 2 hours while the other supports the entire project of human civilization? The rotation is the clue. Not the complete answer, the clue. Because whatever happened to Venus in those early billions of years left a signature in the way it turns. And that signature is written backwards, in a direction that should not exist without something enormous having acted on it. There is a pause in the dark before we go further. Take it. Let the twins sit side by side in your mind for a moment before we go to the event that separated them. When scientists look for what broke Venus's rotation, the first place they look is the event that disrupted Earth's rotation too. Not completely. Earth still spins counterclockwise, still carries its inherited motion, but Earth was struck hard, and the evidence of that strike has been orbiting above every person who has ever looked at the night sky. The moon is a scar. The giant impact hypothesis is the current scientific consensus for how the moon formed. It is worth understanding in careful detail before applying its logic to Venus, because it establishes that impacts of this scale are not theoretical. They happened. The evidence is orbiting 384,000 kilometers above your head right now. Roughly 5 billion years ago, when the solar system was less than 100 million years old and the inner planets were still being bombarded by debris from the formation process, a body called Theia collided with the early Earth. Theia was not a small object. Current models place its mass somewhere between that of Mars, which is roughly 11% of Earth's mass, and an object nearly the size of Earth itself, depending on which simulation you run. It was a protoplanet in its own right, a world that had formed, differentiated into a core and mantle, developed its own geological processes, orbited the Sun in the same general region as the early Earth. The collision was not a gentle encounter. Models suggest it was an oblique impact, not head-on but at an angle, at a relative velocity of roughly 4 to 6 kilometers per second. At that speed and at those masses, what happens is not what everyday experience suggests. Rock does not simply crack or crumple. At the point of impact, the kinetic energy is so enormous that rock on both worlds was converted to vapor and plasma in the first fractions of a second. A vast cloud of vaporized material was ejected from the collision zone at velocities high enough to escape the surface, but not high enough to escape the Earth-Moon gravitational system entirely. That cloud spread into a disk around the early Earth. Over tens of thousands of years, a geological eye blink, less time than human civilizations have been keeping written records, gravity pulled the scattered material together. Piece by piece, the disk coalesced. The moon assembled itself from the wreckage of a collision that should, by any intuitive measure, have been the end of everything. Let's take this further. The impact did multiple things to Earth simultaneously, and each of them echoes into the present in ways that are difficult to overstate. Earth's axial tilt was set by Theia. Before the collision, Earth's rotation axis may have been nearly perpendicular to its orbital plane. Very little tilt, very little seasonal variation. After Theia, Earth sits at 23. 4 degrees of tilt. At 23. 4 degrees is the reason summer in the northern hemisphere brings longer days and more direct sunlight. It is the reason winter brings shorter days and angled light. It is the reason for every season you have ever experienced, for the migration of every bird that has ever flown south for winter, for the agricultural calendars that allowed the first civilizations to predict planting seasons and store enough food to survive the cold months. The entire seasonal architecture of life on Earth traces back to the angle of one impact. For Theia, 5 billion years ago, the impact also changed the length of Earth's day. Earth was rotating much faster before Theia. Some models suggest days as short as 5 to 6 hours. The collision slowed it significantly, and the moon's ongoing tidal drag has been breaking Earth's rotation ever since, adding approximately 1.4 milliseconds to the day every century. In the time since the Roman Empire fell, roughly 1500 years, Earth's day has lengthened by about 21 milliseconds. Undetectable in a human lifetime, across geological time it has transformed a 6-hour day into the 24-hour day that the entire biological architecture of life on Earth has evolved around. Now consider, what if something comparable or larger struck Venus? The giant impact theory for Venus proposes that during the same era of heavy bombardment, something large struck Venus. The exact requirements are different from Theia, because the goal is not to produce a moon, but to reverse a spin, and the geometry that reverses a spin is more constrained than the geometry that produces a moon. Here is the mechanics with full precision. Angular momentum can be transferred between bodies during a collision. If an impactor strikes a planet in the same direction as that planet's existing rotation, it adds to the rotation, the planet spins faster. If the impactor strikes from a direction opposite to the existing rotation, it subtracts from the rotation. If it has enough mass and enough velocity in that opposing direction, it can slow the rotation to zero. And if the remaining dynamics of the collision push further, the rotation can reverse. The word reverse needs to be defined precisely. A single impact would not flip a planet's spin like a light switch being toggled. What it would do is this: it would slow the existing counterclockwise rotation dramatically, grind it from whatever vigorous pace Venus originally spun at, down to something sluggish and fragile. And then with that depleted rotation barely holding on, the continuing dynamics of the impact aftermath could push it further. The redistribution of mass within the planet. The response of the atmosphere. The ongoing gravitational interactions with the Sun. Over millions of years, the wounded, slow rotation could tip over into a new equilibrium, a slow clockwise crawl, the one we observe today. Computer simulations of this scenario have become increasingly detailed as computing power has grown. Multiple research teams have run them, adjusting the impact to mass, the angle of impact, the velocity, the initial rotation rate of Venus, searching for the family of solutions that produces the retrograde Venus we observe. The results consistently show that it is physically achievable. An impactor with a mass somewhere between 10 and 50% of Earth's mass, arriving at the correct angle and opposing the original spin, produces a planet whose rotation matches what we observe in Venus today. Now let's push to the absolute limit of this idea. What if it was not one impact, but a sequence? The early solar system's first billion years, the period called the Late Heavy Bombardment, was not an era of one catastrophic event and then calm. It was sustained violence. Large bodies were still clearing orbital lanes, colliding, merging, being ejected. Some models suggest that Venus may have received a series of large impacts rather than a single event, each one further disrupting the rotation, each one making it harder for the planet to recover its original spin. The final retrograde rotation we observe today might be the accumulated legacy of several catastrophic events, each one ratcheting the spin further from its starting point. This is not proven. It is a family of models, but it fits the general violence of the era, and it helps explain why Venus's rotation is as slow as it is, slower than any single impact model comfortably produces on its own. And yet the impact theory alone cannot close the case. Here is why. Venus has no moon. Earth has the moon as evidence of Theia. The moon is not a philosophical comfort. It is a physical constraint that allows scientists to test models of the impact. The moon's composition, its orbital characteristics, the ratio of certain isotopes within it, all constrain what Theia must have been. Venus has no natural satellites, not even a small irregular captured body. Whatever struck Venus, if something did, either struck in a configuration that produced no moon or produced a moon that was subsequently lost. A mechanism for losing a Venusian moon exists. Venus's proximity to the Sun means any moonlet would experience intense solar tidal forces. These forces could have destabilized the orbit over millions of years, causing the moon to spiral inward until it was destroyed by Venus's gravity, or outward until it escaped entirely. Some calculations suggest a Venus moon could have been eliminated within 10 to 200 million years of its formation. This is not impossible, but it is an additional layer of assumption, and the surface tells us nothing. After 5 billion years of volcanic activity so intense that scientists believe the entire Venusian crust was replaced by new lava flows sometime between 300 and 600 million years ago, any physical evidence of an ancient impact, the shocked quartz that forms under impact pressure, the iridium layers left by extraterrestrial impactors, the ancient impact basin has been erased, repaved, melted and recast into new rock. If the Venetian surface were a crime scene, every wall has been knocked down and rebuilt. The floors are new. Whatever evidence existed has been turned into something else. What we have is a theory supported by physics and by analogy with events we know occurred elsewhere in the solar system, with no surviving physical evidence to confirm it directly. That is not a failure. It is the honest accounting of what 5 billion years of planetary violence does to the record. The impact theory requires a moment, a catastrophic event, brief on geological timescales, that redirected the spin of an entire world through sheer force. The second theory requires no moment at all. It requires only time, and an atmosphere, and a patience so vast that describing in years becomes almost meaningless. You already understand tides in the most intuitive sense. The moon pulls on Earth's oceans. It creates two bulges of water, one on the side of Earth facing the moon, one on the opposite side, and these bulges travel around the planet as Earth rotates beneath them. Every coastal tide you have ever seen, every tidal chart on every harbour entrance in the world, is the moon's gravity acting on water over a distance of 384,000 kilometres. But the ocean is not the only fluid that responds to gravitational influence. The atmosphere responds too. The sun's heat warms Earth's dayside atmosphere, causing it to expand. This creates a slight atmospheric tide, a bulge of marginally denser, warmer air that migrates around the planet. On Earth, this effect is tiny, completely dwarfed by the ocean tides from the moon and the solid body tidal effects from both the moon and the sun. But it exists. It has been measured. It is real. Now build a planet where that atmospheric effect is not tiny at all. Give it an atmosphere 90 times denser than Earth's. Remove the ocean that absorbs most of Earth's tidal energy. Remove the moon whose gravitational presence dominates all other tidal signals. Place the planet closer to the sun. Venus orbits at about 72% of Earth's distance, which means it receives about twice the solar radiation per unit area. The atmospheric thermal tide that is a whisper on Earth becomes on Venus something much more significant. The atmospheric tidal theory works through a mechanism called thermal tidal torque. The term deserves careful definition because it is worth understanding precisely. Torque is rotational force. Think of a wrench on a bolt. You push straight down on the wrench handle. The wrench converts that linear force, your push, into rotational force on the bolt. The bolt turns not because you twisted it directly, but because the wrench transferred the force through leverage into rotation. Torque is the rotational outcome of a force applied at a distance. Now apply this to an atmosphere. The sun heats Venus's dayside atmosphere. The heated air expands, becomes slightly less dense, and shifts. It redistributes itself around the planet in a pattern driven by the solar heating. This redistributed atmospheric mass is not perfectly symmetric around Venus. It bulges slightly on the dayside, and that asymmetric atmospheric mass exerts a gravitational pull on the planet beneath it. The planet is not perfectly spherical either, and gravity between these two non-spherical bodies creates a torque, a tiny, persistent, unceasing rotational force acting on the planet through its own air. In this picture, the sun is the hand on the wrench handle. The atmosphere is the wrench. Venus is the bolt being turned, very slowly by a force that never stops, across billions of years. Here is a concrete case that makes this real. The moon is tidally locked to Earth. It rotates exactly once on its axis for every orbit it completes around Earth. This is why we always see the same face of the moon, the near side with its familiar dark maria, the far side we never see from Earth without spacecraft. The moon was not always this way. Early in its history, the moon rotated faster, showing different faces to Earth at different times. But Earth's gravity acted on the slight asymmetries in the moon's mass distribution. The same torque mechanism operating gravitationally through solid rock rather than through an atmosphere. And over hundreds of millions of years, it slowed and synchronized the moon's rotation with its orbit. The moon is now tidally locked. A stable equilibrium arrived at slowly, through an unimaginable accumulation of tiny forces. The atmospheric tidal theory proposes that the sun has been doing something similar to Venus, but working through the atmosphere rather than through gravitational action on the solid body directly. Let's take this further. The atmospheric tidal model has a specific testable prediction if the process has been running long enough to produce the current rotation. Venus's spin should have settled into a resonant relationship with its orbital period and with its closest approaches to Earth. And indeed, every time Venus comes to inferior conjunction, its closest approach to Earth when it passes between Earth and the Sun, Venus presents almost the same face toward Earth. The rotation period of 243 Earth days fits neatly into a near resonance with the Venus-Earth synodic period of about 584 days. This is the kind of near-integer relationship that tidal processes tend to produce as they lock systems into stable resonances. It is not conclusive proof, but it's exactly what the atmospheric tidal model predicts, and it is difficult to explain otherwise. Now let's push to the most extreme version of this process. Consider what it would have taken to bring Venus from a counterclockwise rotation similar to Earth's, around 24 hours per rotation, to the current 243-day retrograde rotation. The calculation is as follows. To reverse the rotation from a 24-hour counterclockwise spin to a 243-day clockwise spin, so you need to remove an enormous amount of angular momentum, bring the rotation to zero, and then rebuild angular momentum in the opposite direction. The atmospheric tidal torque required to do this across a reasonable planetary timescale, say 2 to 4 billion years, is consistent with what Venus's dense atmosphere can plausibly produce, given what we know about its mass and the solar heating it receives. 2 to 4 billion years. During the middle span of that range, life on Earth was progressing from the first multicellular organisms through the Ediacaran period strange soft-bodied animals. During the later part of that range, the Cambrian explosion was producing the first complex animal body plans. Vertebrates were evolving, fishes were developing, amphibians were crawling onto land, dinosaurs were rising and going extinct, mammals were diversifying, primates were diverging, humans were arriving. All of that history, the entirety of complex animal life on Earth, may have unfolded in roughly the same period that Venus's atmosphere was completing the final stages of reversing the planet's spin. A planet being turned the wrong way by its own air, slowly, persistently, without pause, across the whole span of animal life on another world. The atmospheric tidal theory has a specific observational fingerprint that makes it more than a hypothesis constructed purely from theory. It makes a prediction that can be checked against what we actually measure. The prediction is this. If the atmospheric thermal tide has been acting on Venus for billions of years and has produced the current rotation as a stable equilibrium, then the rotation period should be in a resonant relationship with Venus's orbital geometry around the Sun. And specifically, it should produce a pattern in how Venus presents itself to Earth at each closest approach. Here is the check. Venus reaches inferior conjunction, its closest approach to Earth, roughly every 584 days. If you measure which face of Venus is turned toward Earth at each inferior conjunction, and compare it across multiple conjunctions, you find something that is not random. Venus presents almost the same face toward Earth at each closest approach, rotating at a rate that produces a near-integer relationship with the Venus-Earth synodic period. This is what tidal resonances look like. The Moon-Earth system produces the same kind of near-integer relationship. Io, Europa, and Ganymede, 3 of Jupiter's moons, are locked in a resonance where for every orbit Ganymede completes, Europa completes 2, and Io completes 4. These are the signatures of tidal processes that have run for long enough to lock systems into stable resonant states. Venus's rotational resonance with its Venus-Earth geometry is not as clean as those examples. It is approximate rather than exact. But the approximation is close enough that random chance is a very poor explanation for it. The atmospheric tidal model predicts this near resonance as a natural outcome of the locking process, and the data shows the near resonance is there. This is not proof that the atmospheric tidal mechanism is responsible, but it is the kind of agreement between prediction and observation that gives a theory credibility beyond the mere possibility that the mechanism works. Now consider the energy budget of the atmospheric tidal process, because the scale of what is required is worth sitting with. To reverse Venus's rotation from a counterclockwise Earth-like spin to the current clockwise 243-day retrograde rotation, the atmospheric tidal torque needed to remove and then rebuild an enormous amount of angular momentum. The total angular momentum of Venus's current rotation is approximately 1.5 times 10 to the 29th kilogram meters squared per second. The torque required to change this over a timescale of 2 to 4 billion years works out to a force that, while tiny on any human scale, is applied continuously for longer than the entire history of complex animal life on Earth. Tiny force, unimaginable duration. The product of those two things is the world we are describing. The weakness of the atmospheric tidal theory, as with the impact theory, is the problem of the missing early record. For the model to work starting from an Earth-like rotation, the early Venusian atmosphere needed to have been thick enough to produce the required torque during the critical early period, the first billion years or so, when the rotation was most vulnerable to reversal. We do not have a direct measurement of what Venus's early atmosphere looked like. Venus's current atmosphere is the result of billions of years of volcanic outgassing, photodissociation of water vapor, loss of hydrogen to space, and the accumulation of carbon dioxide from both volcanic sources and from the breakdown of carbonates that were once dissolved in whatever water Venus had. The composition of the early atmosphere is constructed from physical reasoning and from comparison with what we know about Earth's early atmosphere, which is itself only partially understood. What we can say with reasonable confidence is that Venus's atmosphere was likely thicker than Earth's very early in its history. Venus is closer to the Sun, receives more heat, and would have had more vigorous volcanic activity in its early period. A thicker early atmosphere means more atmospheric tidal torque, which means the process we are describing was more efficient in the early period than it is now. The early solar system, in other words, may have been the most efficient time for the atmospheric mechanism to act on Venus's rotation, and the early solar system was also the time when the impact or impacts occurred. The two mechanisms may have been most active at approximately the same time, compounding each other's effects in the period when Venus's rotation was most vulnerable. Hold that for a moment. The weakness of the atmospheric tidal theory mirrors the weakness of the impact theory. The evidence is missing. For the atmospheric torque model to have worked, starting from an Earth-like rotation, Venus's early atmosphere needed to have been dense enough to produce the required torque during the critical early period. We do not have a direct measurement of what Venus's early atmosphere looked like. We are inferring backwards through billions of years of geological and atmospheric change that we cannot directly observe. The early atmosphere is, at present, a hypothesis constructed from physical reasoning rather than direct evidence. Two theories, both grounded in real physics, both supported by calculations that show the mechanism works, neither with the direct evidence needed to close the question on its own. Neither theory is sufficient alone. Both together may be exactly right. This is where most planetary scientists who focus on Venus currently sit, not in one camp or the other, but in the uncomfortable and honest position that Venus's retrograde rotation is probably the result of both mechanisms working across vastly different timescales, and we cannot yet measure where one ended and the other began. Here is how the combined model works in its full form. In the early solar system, during the first 500 million to 1 billion years, while the late heavy bombardment was still active and the inner planets were still sweeping up the debris of formation, Venus was struck by one or more large impactors. These impacts did not necessarily reverse Venus's spin on their own. What they did was disrupt it, slow it down, remove a significant fraction of the original angular momentum. Take the robust, fast counterclockwise rotation that Venus inherited from the solar nebula and replace it with something wounded, slow, tilted, unstable. Picture it concretely. Venus began with perhaps a 24-hour rotation, similar to Earth's current rotation, comfortable, stable, carrying the full angular momentum inheritance of the solar system. After the impact or impacts, it had something much slower, perhaps a rotation of several weeks, perhaps several months, perhaps tilted into an orientation that was no longer cleanly counterclockwise but somewhere between directions, not yet reversed, but fragile. Then the atmosphere took over. For the following 4 billion years, during the entire history of complex animal life on Earth, from the first Ediacaran organisms through every extinction event and every recovery through the Cambrian, the Devonian, the Permian, the Jurassic, the Cretaceous, the Paleocene, and every era since, the atmospheric tidal torque was working on Venus, without pause, without rest, pushing the slow wounded rotation further. first bringing it to a complete halt. A moment, spread across millions of years, when Venus was not rotating at all relative to the Sun. Then, gradually, building a new rotation in the opposite direction, slowly growing the clockwise spin from nothing until it settled into the slow resonant pattern we observe today. The combined model has an advantage neither theory alone possesses. It requires less from each mechanism individually. The impact does not need to have been powerful enough to reverse the spin entirely on its own. It only needs to have disrupted the rotation and slowed it significantly. The atmospheric torque does not need to have been strong enough to reverse a fast-spinning planet from scratch. It only needs to have been strong enough to push a slow, disrupted, unstable rotation the rest of the way over. Two smaller catastrophes, working together, achieve what neither could achieve alone. Now let's push to the absolute limit of what this combined model implies. If this picture is correct, then the retrograde rotation of Venus is a process that has been unfolding across the full history of the solar system. The impact, or impacts, occurred in the first few 100 million years. The atmospheric torque has been running since then. 5 billion years of accumulated physics, summing to a single observable outcome, a planet spinning backwards. And critically, both mechanisms are now invisible. The impacts left no moon. The geological record has been wiped by volcanic resurfacing. The atmospheric torque leaves no permanent signature that distinguishes itself from the normal thermal evolution of the Venusian atmosphere over billions of years. We are looking at the final state of a process that ended in the sense of reaching its current stable equilibrium, probably within the last billion years, and which began 5 billion years ago, and which destroyed its own evidence at every stage. The question of proportion. How much did the impact contribute? How much did the atmosphere contribute? May be permanently unanswerable with current evidence. Future missions will tighten the constraints. Da Vinci Plus, NASA's planned atmospheric probe, will measure the composition and structure of the Venusian atmosphere at different altitudes, giving us a far more detailed picture of the atmospheric dynamics and the history of its chemistry. Envision, the ESA radar mapping mission, will image the Venusian surface at higher resolution than any previous mission, potentially revealing geological features that survive from the ancient terrain. These missions will not directly answer the rotation question, but they will provide the constraints that the models need to become more precise. For now, what the science honestly says is this: something terrible happened to Venus long ago, almost certainly more than one thing. The mechanisms that caused it are understood in their physics, supported by calculations, and consistent with the orbital evidence we have. The specific events, the impactor's mass and angle and timing, the early atmospheric density, the exact path of the reversal, are lost. The combined model, impact plus atmospheric torque, has a specific implication for what future missions to Venus should look for. If the impact component was real, the ancient highlands of Venus, the tesserae, the oldest terrain on the planet, should show evidence of a surface that formed under conditions very different from the current volcanic resurfacing cycle. The composition of the tesserae, if they are accessible to chemical analysis from orbit or from a lander, should tell us something about the early history of the crust. If the crust formed in the presence of water, which granite-like compositions would suggest, that is evidence that the early Venus was a fundamentally different world, and the transition to what it is now was driven by a change in conditions, possibly including the rotation change and its effect on the atmospheric dynamics. The atmospheric torque component has its own observational target, the detailed dynamics of the current Venusian atmosphere. If the atmospheric tidal mechanism is the mechanism that completed the rotation reversal and is now maintaining the current equilibrium, the atmosphere should show specific patterns of circulation and thermal structure that are consistent with being in that resonant lock state. Da Vinci Plus's atmospheric probe will measure the chemistry and temperature structure of the atmosphere at different altitudes during its descent, giving the first detailed profile since the Venera probes. That profile will constrain the current state of the atmospheric dynamics in ways that will allow better modeling of whether the thermal tidal torque is, in fact, what the models predict it to be. There is a broader scientific context for why Venus matters beyond its own history. Exoplanet science. The study of planets around other stars has identified dozens of planets in the so-called habitable zone of their stars that are roughly Earth-sized or Venus-sized. We cannot directly measure the rotation rates of most of these worlds. We cannot measure their atmospheric compositions in most cases, but we know that some of them will be in configurations similar to early Venus, same size, similar distance from a similar star, and some of them will have experienced similar impact histories and similar atmospheric evolutions. Understanding what happened to Venus gives us a template for what might happen to other Venus-like worlds in other solar systems. The question of how common the Venus outcome is versus the Earth outcome is one of the most important questions in astrobiology, the study of where and how life might exist in the universe. If most Venus-like worlds end up like Venus rotation reversed, water lost, greenhouse runaway, then the window of habitability for Earth-sized planets may be narrower than optimistic estimates suggest. If the Earth outcome, rotation preserved, water retained stable climate, is the exception rather than the rule, then the fact of life on Earth becomes more significant rather than less, not because the universe intended it, but because the specific combination of events that allowed it was less probable than a simpler accounting would suggest. The angle of an ancient impact, multiplied across billions of potentially similar planetary systems, becomes a question about how common life is in the galaxy. If you are still with us this far into the night, a quiet like or subscribe before we continue helps this channel reach more people who might need exactly this kind of evening. It is a small thing. It matters more than it looks. Sail inward from Earth, cross the space between the two planets at their closest approach, a distance of about 41 million kilometers, which at the speed of the New Horizons spacecraft, the fastest probe ever launched from Earth, would take roughly 3 months to cover. Pass through the region where Venus's induced magnetosphere meets the solar wind, and then enter the atmosphere. The top of the Venusian cloud deck sits about 65 kilometers above the surface. Up here, the pressure is similar to Earth's at sea level. The temperature is between 30 and 70 degrees Celsius warm, but livable. There is sulfuric acid in the air in every direction. But in terms of pure physical conditions, pressure and temperature, this is the closest thing to Earth-like that exists anywhere on Venus. This layer is the one where some researchers have raised the theoretical possibility of microbial life. Not life on the surface, but life floating in the upper cloud layers, where the physical conditions are merely unpleasant rather than immediately lethal. The idea is contested. The chemistry does not yet support it clearly, but the fact that it has been raised at all by serious scientists working from physical reasoning rather than optimism tells you something about how thin the margin is between habitability and its absence. Descend further. At 50 kilometers altitude, the pressure has risen to about 1,000 kilopascals, 10 times Earth's surface pressure. The temperature is 75 degrees Celsius. An unprotected human would not survive here, but not because of physics alone. The sulfuric acid would reach you before the pressure became critical. At 30 kilometers altitude, the pressure is 4,000 kilopascals and the temperature is 285 degrees Celsius. Lead is still solid here, just. Zinc is approaching its melting point. Tin is already liquid. At the surface, 9,200 kilopascals, 465 degrees Celsius. Every metal you routinely encounter, tin, lead, zinc, bismuth, the solder in your electronics, is liquid. Aluminium, the metal in your kitchen foil and your aircraft fuselage and your soft drink cans, requires only another 200 degrees before it too becomes liquid. The rock itself, in the lowest valley regions, may be near its softening temperature in some locations during local afternoon. The Soviet Venera program is the only one in history to have successfully placed spacecraft on the Venusian surface and returned data from there. Between 1970 and 1985, a series of increasingly sophisticated probes was sent to the planet. The engineering philosophy was not elegant optimization, it was brute force survival. The landers were built like bathyspheric diving bells, like the submersibles that explore the deepest ocean trenches on Earth. They were not expected to last long. They were expected to survive entry, reach the surface and transmit whatever they could before the heat and pressure killed them. Venera 7, in December 1970, became the first spacecraft to transmit data from the surface of another planet. It survived for 23 minutes before going silent. In those 23 minutes, it confirmed the surface temperature and pressure measurements that previous flyby missions had estimated. Confirming. for the first time with direct surface measurements, just how extreme the conditions were. Venusian 9 in October 1975 returned the first photographs of the Venusian surface. The images showed something that surprised geologists: angular, freshly broken rock slabs with sharp edges lying in piles. The sharpness of the edges meant the rock had not been rounded by the kind of wind erosion and thermal cycling that rounds exposed rock on Earth over long periods. The surface, geologically speaking, was young. The rock had not been sitting there long enough to weather. Venus 13, landing on March 1, 1982, transmitted for 127 minutes before the planet destroyed it. In those 187 minutes, it returned the first color photographs of the Venusian surface and drilled a core sample of the soil for chemical analysis. The photographs showed a flat, rocky plain, basalt slabs, an orange-yellow sky, the color of sunlight filtered through 30 kilometers of dense cloud. The light level on the surface of Venus is similar to an overcast day on Earth. Not dark, just heavy, filtered, enclosed, 127 minutes. That is the duration of a feature film. It is the time between a late dinner and midnight. It is how long the most successful probe in the history of Venusian surface missions survived before the planet destroyed it. No spacecraft has landed on Venus since 1985. The engineering challenge of building something that can survive significantly longer has not yet been met. The engineering problem of surviving on Venus is worth stating precisely, because it is not simply a matter of making a spacecraft heat-resistant. It is a simultaneous multi-system problem that compounds in ways that has defeated every engineering approach tried so far. The heat destroys conventional electronics, high-temperature electronics, made from silicon carbide rather than standard silicon, can operate at temperatures up to about 500 degrees Celsius, just above the Venusian surface temperature. But the sulfuric acid in the atmosphere corrodes the materials that would house those electronics. The pressure crushes conventional pressure vessels unless they are extraordinarily thick, and thick walls mean heavy spacecraft, which means more fuel needed to land, which means larger descent stages, which means more complexity and more potential failure points. Each solution to one problem creates or worsens another. The planet resists engineering the way a simultaneous equation with more constraints than variables resists a clean solution. NASA has proposed a mission called LLISSE, the Long-Lived In-Situ Solar System Explorer, designed to use high-temperature electronics and a titanium pressure vessel to target surface survival times of 60 days rather than 127 minutes. If it succeeds, it would be the longest Venus surface mission in history by a factor of roughly 700. 60 days would allow continuous monitoring of atmospheric chemistry, wind patterns, seismic activity, and surface conditions through a full Venusian day-night cycle. It would transform our picture of the surface dynamics in ways that the Venera missions, operating under pressure to transmit before dying, could not. And yet, even 60 days is a small window in a world whose history spans billions of years. What such missions will give us is a snapshot of the present state from which we can build better models of the past. The past itself, the Venus that may have had oceans, the Venus whose rotation was being reversed, the Venus that might have been a living world, remains accessible only through inference, through radar maps that show the oldest terrain, through spectral measurements that hint at water-formed minerals, through the physics of angular momentum that says the rotation we observe could not have been there from the beginning. And yet, buried in the radar maps that have been built from orbit, there are hints of something that existed on Venus before any of this. Before the current inferno, before the acid clouds and the crushing pressure and the orange light. Hints of a world that was once, possibly, very different. Some planetary scientists believe that Venus may have had liquid water in its early history. The evidence is indirect and contested, but it is persistent. Certain ancient highland regions on Venus, the tesserae, which are the oldest terrain on the planet, heavily deformed and chemically distinct, have spectral characteristics that suggest mineral compositions which on Earth form only in the presence of liquid water. Granites and related rocks require water as part of their formation process. If the tesserae contain granitic material, as some spectral data suggests, they may represent the remnant of an ancient crust that formed when water was present. Climate modeling has added to this picture. A 2019 study using a three-dimensional climate model with realistic topography found that Venus, with a somewhat slower initial rotation rate and a cloud distribution similar to what the model produced, could have maintained surface liquid water for somewhere between 2 and 3 billion years. 2 to 3 billion years of liquid water on Venus. For comparison, the oldest confirmed evidence of life on Earth dates to about 5 billion years ago, and life is believed to have begun within the first billion years. 2 to 3 billion years of liquid water, given the right chemistry, is more than enough time for life to begin. We do not know if life began on Venus. We do not know with certainty if the liquid water existed. We are working at the absolute edge of what orbital radar and spectroscopy and climate modeling can tell us about a world that may have completely erased its own ancient record through volcanic resurfacing. But the possibility exists. 2 identical worlds, one of them possibly with oceans. Chemistry running in water. The conditions that, on Earth, led to everything, and then something changed, perhaps triggered or accelerated by the same impact or series of impacts that disrupted the rotation, and the feedback loop tightened. Temperature rose. Water began to evaporate. Water vapor in the atmosphere trapped more heat. Temperature rose further. More water evaporated. The feedback continued until the oceans boiled entirely. The water vapor was broken apart by solar radiation. The hydrogen escaped to space, and what remained was a planet with no water, no moderating influence, and a carbon dioxide atmosphere that trapped heat until it reached 465 degrees. Venus did not choose this. Physics chose it, given the initial conditions and the events that disrupted them. And somewhere underneath all of it, underneath the acid clouds and the crushing pressure and the orange light and the melting metals and the 127-minute survival limit, Venus is still turning, slowly, the wrong way. The sun crawling from west to east across a sky no human being has ever seen directly, and which, given the current state of engineering, none will see directly for a very long time. Earth was in the same solar system during the late heavy bombardment. Earth was in the same region. Earth was struck by Theia, which was larger, by most estimates, than the impactor that current models require to have disrupted Venus. And Earth survived with its rotation mostly intact. Tilted, yes. Slowed, yes. Changed in fundamental ways, yes. But still counterclockwise, still carrying its inherited motion. Why? The answer is geometry. The angle of Theia's impact on Earth was such that it added angular momentum in a direction broadly compatible with Earth's existing rotation, rather than opposing it. Theia did not strike head-on against Earth's spin. It came in at an angle that transferred angular momentum in the same general direction Earth was already turning. The impact slowed Earth somewhat, changed its tilt, launched the Moon into orbit, but it did not reverse the spin. If Theia had arrived from a slightly different direction, if the gravitational interactions that shaped Theia's trajectory over its lifetime had produced an approach angle that opposed Earth's rotation rather than complementing it, the outcome would have been different, not necessarily Venus-like. There are too many variables to say that with certainty, but different, potentially very different. Now, take this further and hold it carefully. What would a retrograde Earth look like? A retrograde rotation would reverse the Coriolis effect that currently drives Earth's large-scale atmospheric circulation. Trade winds blow from east to west in the tropics because Earth's rotation deflects moving air masses to the right in the northern hemisphere and to the left in the southern hemisphere. A retrograde Earth would flip those deflections. Trade winds would blow in the opposite direction. Ocean circulation patterns, which are tightly coupled to the winds and to the Coriolis effect, would reverse. The distribution of warm and cold water across the ocean basins would change. Some climate modeling of retrograde Earth suggests that the distribution of precipitation would shift significantly, some currently arid regions becoming wetter, some currently wet regions becoming drier. The general zones of habitability would not disappear, but they would be differently located. We do not know whether life would have emerged on a retrograde Earth. We do not know whether, if it emerged, it would have had the same billion-year span of stable conditions that allowed complexity to develop here. The question cannot be answered because we cannot run the experiment, but the question itself is not idle. It is the question of what we are, phrased in terms of geometry. Now let's push to the absolute limit. What if the collision that gave Earth the Moon had been more directly opposed to Earth's rotation? What if it had been more like whatever struck Venus? What if Earth had ended up with a retrograde rotation, a destabilized atmosphere, and the same cascade that stripped Venus of its water? There would be no one here to ask the question. That is not a comfortable thought, and it was never meant to be comfortable. Comfort requires the illusion that Earth was always going to be what it is, that habitability was the destination, that life was the direction everything was heading, that consciousness was the inevitable outcome of a universe that had it in mind from the beginning. The geology says otherwise. The geology says that what we have is not the inevitable outcome of an ordered universe, but the specific result of one particular configuration of rocks and trajectories in the early solar system, out of an enormous number of configurations that would have produced something entirely different. Your existence is downstream of a geometry problem, of a rock arriving at one angle rather than another, of the early solar system having arranged the trajectories in one particular way. The philosophical cascade that Venus represents has one more level that is worth following to its end. We have established that Earth's current state, habitable, stable, wet, alive, is the result of specific physical events in the early solar system, and that those events could have been otherwise. Venus is the concrete demonstration that otherwise is not abstract. It is 41 million kilometers away at closest approach. It is the brightest object in the sky after the moon. The otherwise is visible to the naked eye every clear night, hanging in the western sky just after sunset or the eastern sky just before dawn. But there is a further step in the cascade that is worth taking. Not just that Earth's habitability was contingent, but that the contingency matters in a specific way for how we understand our situation. If the conditions for life require a specific combination of events, a particular impact geometry, a particular rotation outcome, a particular atmospheric evolution, a particular history of liquid water stability, then the universe is not generally configured to produce life. It is specifically configured to produce life in the rare places where the contingencies aligned. And those places are rare, not because the universe is hostile, but because the combination of events required is specific. This framing, life arising where the contingencies aligned rather than where the universe intended it, has a particular implication for how we think about the search for life elsewhere. The Fermi paradox asks why, if life is common, we do not see evidence of it everywhere. One answer that Venus makes vivid is this: because the path from a potentially habitable world to an actually inhabited one requires a specific sequence of physical events that may be uncommon. Venus was potentially habitable. It was the right size. It was in the right neighborhood. It had, possibly, liquid water for hundreds of millions of years. And yet, it is empty. Not because it lacked the ingredients, but because something, the impact geometry, the atmospheric evolution, the rotation reversal, removed the conditions before life could establish itself, or removed the conditions after it established itself and before it became complex enough to survive the transition. We do not know which of those it was. We do not know if Venus ever had life, but we know that if it did, it is gone. And the most probable reason it is gone is not exotic. It is the same physics that everywhere governs how planets evolve. The same atmospheric greenhouse physics that keeps Earth warm enough for life ran away on Venus. The same tidal forces that produce predictable ocean tides on Earth reversed Venus's rotation. The same impact dynamics that gave Earth its moon disrupted Venus's spin. The physics is not strange. The outcomes are different because the initial conditions and the specific events were different. The kinetic energy released in any impact capable of reversing Venus's rotation is a number worth grounding precisely. For an impactor with roughly 20% of Earth's mass, in the middle of the plausible range from simulations, moving at a relative velocity of 5 kilometers per second and striking at an oblique angle, the kinetic energy deposited into Venus would be on the order of 10 to the 28th joules. To make that number feel like something, the total energy released by all nuclear weapons ever tested by every nation in history is approximately 10 to the 18th joules. A hypothetical Venus impactor delivered, in a single event, roughly 10 billion times the total nuclear energy ever released on Earth, in a single day of planetary time, into a world the same size as ours. This is not presented to shock, It is presented to anchor the scale of what the physics requires. The rotation reversal of Venus, if it happened through an impact, did not happen through a modest event. It happened through something that melted the Venusian surface, disrupted its interior, and altered the course of that planet's evolution for billions of years afterward, and the only physical record of it is a planet turning clockwise at 243 days per rotation. What Venus offers, in the end, is not a cautionary tale about what happens when a planet goes wrong. It offers something more precise. A demonstration that the difference between a living world and a dead one can be the angle of a rock that no longer exists, that the margin between those two outcomes is not wide, that the universe does not guarantee the conditions for complexity. It allows them in specific places under specific conditions for specific periods. And in those places, in those conditions, for those periods, something like the conversation you are having with the universe right now becomes possible. Take a breath here. Venus is the reminder. The most visible, most present, most concrete reminder we have that habitability is not guaranteed by size or position or composition alone. It is contingent. It depends on history. And history, in the early solar system, was the accumulated outcome of physics acting on specific objects at specific velocities in specific directions, without reference to what any of those outcomes would eventually produce. There is a particular kind of quiet that comes when you have followed a question far enough to reach the edge of what is knowable. It is not the quiet of an unanswered question that might someday be answered with better instruments or more computing power. It is the quiet of a question whose answer has been erased by the very thing the question is about. Venus destroyed its own evidence. The impact left no moon. The volcanic resurfacing erased the ancient geology. The atmospheric transformation that began billions of years ago and has been running ever since has overwritten the conditions that would have told us most clearly what the early Venus looked like. We are trying to read a letter that the sender has burned. And yet we know something happened. We know it the way we know any physical fact, because the alternative requires the laws of physics to be wrong, and the laws of physics are not wrong. Venus is spinning backwards. This is not a measurement artifact. It is real, measurable, confirmed by every spacecraft that has ever flown past or orbited or landed on Venus. And angular momentum does not reverse itself without a cause. Something terrible happened to Venus. The title of tonight's walk was not dramatizing. It was being precise. What that something was, its details, its timeline, the exact contribution of impact versus atmospheric torque, we may never know completely. Future missions will constrain the models further. Future landers, if the engineering is ever solved for extended survival, will tell us things about the surface that radar cannot. Future generations of scientists will build better models and run better simulations. The picture will become clearer. But the complete picture, the frame-by-frame record of what happened in those first billion years when the fate of Venus was being decided, is almost certainly gone. Science is honest about this in a way that takes some getting used to. We expect science to arrive at answers. It is very good at arriving at answers, and it is equally good at identifying the precise edges of where answers cannot yet go. Saying the evidence is insufficient to determine this is not a failure. It is the most accurate statement science can make when the evidence is genuinely insufficient. For the deep history of Venus, in many places, the evidence is genuinely insufficient. But here is what we do know, and what we can hold. We know that Venus and Earth are the same world in different histories, same size, same age, same ingredients. The difference between what they became is not in their nature, it is in what happened to them. And what happened to them was not fixed, not inevitable, not the expression of some deeper necessity in the structure of the universe. It was specific. Contingent, the result of particular trajectories and particular collision geometries on particular days in the early solar system, which could have been otherwise. We know that the early solar system was violent in a way that is genuinely difficult to hold in the mind. The calm arrangement of planets in their lanes that we observe today is the aftermath of an era when worlds were being built and destroyed on timescales of millions of years. The order we see now is not the natural state of solar systems. It is the state that remains after the violence has run its course, and whatever survived has settled into stable orbits. What we call the solar system is the graveyard of everything that did not survive, and the home of everything that did, arranged tidally now that the sorting is over. We know that Venus is still turning. Right now, as you breathe in the quiet and the room holds still around you, Venus is somewhere in the sky. The brightest natural object after the moon, reflecting 70% of all the sunlight that reaches it. Beautiful and opaque, and completely hiding everything behind its permanent cloud cover. It has been turning backwards for billions of years. It will continue turning backwards for billions more. Whatever catastrophe set it in motion is long over. The physics of the reversal is stable now, locked into a slow resonance with the sun. The engineering question, what happened, has a probable answer, even if the details are missing. Impact, almost certainly. Atmospheric torque, almost certainly. Atmospheric torque, almost certainly. Both together, across vastly different timescales, producing the outcome we observe. There is a particular word for what we are doing when we study Venus's rotation, and it is not simply investigation. It is reconstruction. Reconstruction is different from investigation, in that investigation assumes the evidence is present and needs to be found. Reconstruction works from the endpoint backward, through physics and inference, when the direct evidence has been destroyed. A forensic investigator investigating a crime scene collects evidence. A geologist reconstructing the history of a mountain range that has been eroded to its roots is doing something different. They are working from what remains and from what they know about how rock forms and erodes and deforms, to reconstruct a history they cannot directly observe. The study of Venus's retrograde rotation is reconstruction in this second sense. We have the endpoint, a planet spinning backwards at 243 days per rotation. We have the physics, angular momentum conservation, atmospheric tidal torque, impact mechanics. We have the boundary conditions, the initial angular momentum inherited from the solar nebula, the current atmospheric density, the known history of heavy bombardment, and from those elements we reconstruct the most probable path that led from the starting conditions to the current endpoint. The reconstruction tells us something catastrophic happened in the first billion years. The atmospheric torque has been working for most of the solar system's history. The two together produced what we observe, the specific details. The impact is massed to within a factor of 2. The exact contribution of atmospheric torque in percentage terms are beyond what current evidence constrains. This is science working at its honest limit. Not failing, not giving up, working at the edge of what the surviving evidence can tell us, and being precise about where that edge is. And this is why Venus, of all the questions in planetary science, has a particular quality of weight. It is not just a question about one planet's rotation. It is a question about what happens when the evidence of a catastrophic event is almost completely erased by subsequent events. It is a test of whether physics alone, without the direct evidence of the event itself, is sufficient to reconstruct what happened. And the answer is yes, approximately. Probably. To within the constraints of what models with uncertain inputs can tell us. Approximately, probably, to within the constraints. These are not failures of precision. They are the precise language of reconstruction working at its limit. They are as honest as the physics allows. The science of planetary formation has advanced enormously in the last 2 decades, and one of the most important advances is the recognition that the diversity of planetary outcomes is far greater than the solar system alone suggests. Before the era of exoplanet detection, it was tempting to assume that solar systems generally looked like ours. Rocky planets near the star, gas giants further out, the same basic architecture. The first exoplanet surveys demolished this assumption. We have found hot Jupiters, gas giant planets orbiting closer to their stars than Mercury orbits the Sun. We have found super-Earths, planets between Earth's mass and Neptune's mass, with no analogue in our solar system. We have found planets in binary star systems, planets with highly eccentric orbits, planets whose masses and orbital configurations bear no resemblance to anything in our solar neighborhood. Within this diversity, Venus-like outcomes, worlds that started with promise and ended in the runaway greenhouse state, may be common. The physics of the runaway greenhouse is not exotic. It requires only that a planet receive enough stellar radiation to trigger the positive feedback loop between water vapor, temperature, and more water vapor. Planets that are slightly closer to their stars than Earth, or planets around slightly brighter stars at Earth's distance, are candidates for this outcome. Venus sits right at the inner edge of what would conventionally be called the habitable zone around the Sun. It may represent the typical outcome for worlds at this position rather than the exceptional one. If that is correct, if Venus-like outcomes are the norm for inner edge habitable zone worlds, then the question of how common life is in the galaxy becomes more constrained, not because life is impossible at the inner edge, but because the rotation impact greenhouse cascade that converted Venus from a potentially watery world to a lead-melting inferno may be a standard feature of worlds in that position, not a local anomaly. Earth at a slightly greater distance and with the specific impact history it received may be closer to the outer edge of a very narrow band in which the conditions for complex life can persist long enough for it to develop. Venus is the inner wall of that band, made visible, orbiting 41 million kilometers away at closest approach. The philosophical question, what it means, does not have an answer. It has a weight. When we began tonight, I told you that right now, as you settled in and the room went quiet, there was a planet in our sky doing something that should not be physically possible. Venus is spinning backwards. That was where we started. And now, having come through everything we have covered, the solar system's inherited rotation and where it comes from, the identical twins, who became nothing alike, the impact that may have shattered the original spin, the atmosphere that may have finished the reversal over 4 billion silent years, the Soviet probes that lasted 127 minutes in the wreckage of a world that was once possibly wet. That sentence carries different weight than it did when we first said it. It is not a curiosity anymore. It is a consequence, the visible end result of something enormous and violent and now almost completely erased, something that happened in the first billion years of the solar system's existence and left no direct evidence behind except this, a planet turning the wrong way, slowly in the dark. Venus did not always spin backwards. It spun the same way as everything else, once. It came from the same cloud. It inherited the same rotation. And then something happened, something the solar system has not fully disclosed to us yet. Something that reaches across 5 billion years of silence and presents itself in the motion of a world that looks, from a distance, nothing like what it once was. There is a version of the early solar system in which the impactor that struck Venus struck Earth instead, at the same angle, with the same consequence. An Earth with a reversed spin, an Earth whose atmosphere and water inventory followed a different path. An Earth that may have produced something, or nothing, or something entirely unlike what emerged here. We cannot know. We can only know that the Earth we are on is not that Earth, and that the difference is not purpose or design. It is geometry, the direction of something that no longer exists, arriving at an angle that could have been different, on a day 5 billion years ago. You are, in a very literal sense, the result of a deflection, of physics arranging itself in one particular configuration rather than any of the others that were equally available to it. The word deflection is worth sitting with for a moment. A deflection is not an accident, and it is not a plan. It is a physical outcome that depends on the exact initial conditions in a system governed by deterministic laws. If you knew the exact position and velocity of every particle in the early solar system, every atom in every protoplanetary body, every component of the original solar nebula, the exact thermal and gravitational state of every region of space, you could, in principle, calculate the trajectory of the impactor that struck Venus and determine whether its angle was sufficient to reverse the spin. The laws of physics are exact. The outcomes are determined by the inputs. But the inputs were what they were because of the entire prior history of the universe, stretching back 13.8 billion years to the Big Bang. And that prior history is not something we chose or designed or intended. What this means is that your existence here, now, in this room, breathing slowly in the quiet, is the result of 13.8 billion years of physics running exactly as it ran, producing exactly the initial conditions that led to exactly the early solar system, that led to exactly the impact geometry, that led to exactly the impact geometry, that led to exactly the Earth we have. The chain is unbroken. Every link is real. And no link was chosen. This is not a reason for despair. It is a reason for a particular kind of attention. The universe did not produce this moment because it was trying to. It produced this moment because the physics ran this way. And the fact that the physics ran this way rather than some other way that would have produced Venus here and an empty rock where Earth is not something that can be planned for in the future or mourned in retrospect. It is simply what happened. And what happened is you, here, now, listening to a planet turn the wrong way in the dark. Thank you for spending this time here tonight. If these long, careful walks through the universe are what you come here for, a like or subscribe helps this channel find more people who might need exactly this kind of quiet. It means more than it looks. Venus is up there right now, the brightest light after the moon. And here is the last thing worth naming before the night gets fully quiet. The fact that we are asking this question at all, that there are people on this planet who spend their working lives reconstructing the rotation history of a planet 41 million kilometers away from a catastrophic event 5 billion years ago, is itself the consequence of the same physical history we have been tracing: the stable rotation, the tilted axis with its seasons, the moon that stabilizes the tilt, the liquid water that persisted, the billions of years of stable conditions, the emergence of complexity, the development of language and mathematics, and the ability to ask questions about the motion of distant worlds. Venus did not get those conditions, or it lost them before they could produce anything that asks questions. And so there is no one on Venus tonight, reconstructing the impact history of Earth, wondering what would have happened if the geometry had been different. There is only us, here, on the planet where the geometry worked out, asking the question from the inside of the outcome, spinning the wrong way. This is what physics looks like from the inside of one of its outcomes: a planet spinning the wrong way, a moon orbiting the right one, a species on the right one asking why the other turned out differently. The question and the answer and the asker are all part of the same chain of consequences that started with a cloud of gas collapsing 5 billion years ago, with a slight rotation in one particular direction. Good night.